In computational biophysics, relying on standard coding library wrappers to process data carries a hidden mathematical risk. High-level functions condense complex numerical frameworks into a single line of code, abstracting away the physical realities of the systems they are trying to model. Take a standard averaging function, like a NumPy NEM wrapper. It processes every data point with equal weight. If you feed it a dataset of cellular forces, it will output a single average, completely obscuring extreme variances hiding within the raw numbers. This visualization compares a standard array output to the raw data it obscures. On the left, the wrapper calculates an average force value of 18 million, but the raw scatter plot reveals reality. One healthy protein has a force ratio of 145 million, while 7 diseased proteins cluster near just 8.7. The single healthy protein dominates the calculation by 7 orders of magnitude. Accepting the wrapper's condensed average masks the massive loss of structural force in the diseased cells. To capture accurate microenvironmental forces, these high-level statistical abstractions have to be stripped away. The data must be evaluated through explicit, pure math frameworks that calculate every physical interaction at the base level. Relying on statistical wrappers turns biological models into mathematical illusions. Accurate modeling requires explicit, base-level deconstruction. This requirement drives the quantum gene modulation engine. It is a custom, pure math framework designed as a strict alternative to black box deep learning. Instead of approximating patterns, the engine calculates deterministic physical laws, mapping atomic-scale quantum state instability all the way up to macroscopic neural resonance. This diagram models the two diametrically opposed pathologies the system processes. On the left, Alzheimer's disease, characterized by an overactive apoptosis or cell death trigger. On the right, cancer, which actively blocks apoptosis to survive. By calculating explicit Coulombic pair partitions, the exact electrostatic charge interactions across a DNA sequence, the engine calculates a mathematical bridge between oncology and neurodegeneration. The ultimate objective of this framework is to analyze the quantum state collapse of a metastatic cancer cell to expose a highly specific, deterministic target. Standard models often treat genetic mutations as simple, static errors within a biological sequence, missing the dynamic reality. The engine calculates the explicit force of charge 1 against charge 2 across a localized 49 base pair window. This tracks how environmental stress physically warps the DNA. In the Alzheimer's microenvironment model, the engine establishes a baseline examining the APP gene under specific stress conditions, a localized pH of 6.8, and chronic oxidation. This graphic contrasts the two disease states. On the left, Alzheimer's conditions drive the APP gene's LDDM value into a stabilized, deep negative trajectory, reaching negative 1.058. The right side models the cancer microenvironment, targeting TP53 at a 6.5 pH. Here, oxidative stress forces a 6.1% leap in electrostatic repulsion, pushing the LDDM value into positive territory, hitting positive 0.939. As a biophysical consequence of this positive swing, the structural fidelity of the mutated protein drops to 0.252. This structural deformation mathematically defines the tumor's apoptosis blocking mechanism. Extreme environmental stress physically shapes opposite, measurable electrostatic force fields for each disease. By tracking these exact microforces upward to macroscopic neural brainwave signals, the engine revealed an anomaly in the data. This chart visualizes brainwave resonance. Despite opposing physical outcomes, the cancer and Alzheimer's states produce nearly uniform neural coherence signatures, aligning at 0.714 and 0.704. Because the frequencies are identical, the system calculates a 0.95x theta inverse potential. The engine routes this calculation through an entangling layer, using controlled Z gates to act as a mathematical mirror. This operation phase inverts the excessive Alzheimer's cell death signal into a tightly focused targeting vector. The new vector is calculated to perfectly pierce the 71.9% apoptosis evasion threshold of the tumor cell. By calculating exact phase inversions, neurodegenerative structural decay can be mathematically repurposed to neutralize the tumor's apoptosis block. Recent telemetry shows the engine can now generate direct, standalone cancer-targeting signals that no longer depend on the Alzheimer's phase inversion. This is achieved by tracking the internal dynamics of specific folding mutations, like the TP53R175H variant, as it progresses through escalating disease stages. This data table tracks the mutation's progression. By the aggressive metastasis stage, the microenvironment drops to a highly acidic 6.5 pH, and apoptosis resistance skyrockets to 99.8%. Notice the internal DNA base force values. To maintain extreme resistance, the tumor trades structural integrity for survival, cutting the internal structural force from 119 to 59. Concurrently, the external force required to trigger an apoptosis signal explodes, rising from 12 up to 600. In order for a tumor to achieve near-total apoptosis resistance, it must decay its own internal architecture. This structural sacrifice creates highly unstable, deeply targetable points within the genetic sequence, mathematically identified as weak islands. To target these weak islands, the analysis moves down to the absolute base layer, the explicit penny lane quantum state coupling data. Assuming advanced metastasis equates to quantum chaos and biological noise is wrong. The quantum telemetry proves the opposite. Aggressive tumors become highly rigid. This line chart tracks Shannon entropy. As the tumor scales to aggressive metastasis, entropy drops significantly, falling from 4.15 down to 3.95 bits. Thermodynamically, this drop indicates structural collapse has forced the mutant gene into a defined, rigid, low-entropy eigenstate. This rigid state systematically strips away the high-energy guanine and cytosine contact regions across the DNA sequence. Metastatic progression minimizes its own wave function dispersion. It creates a precise, low-entropy profile that is highly susceptible to external targeting. Guanine and cytosine bases act as the primary anchor points, maintaining the structural integrity of the TP53 binding domain. By stripping these contact regions away, the tumor's low-entropy state isolates the remaining guanine bases, turning them into massive, unshielded target vectors. This chart isolates the signal potential of the remaining bases. Targeting a single guanine base causes the value to spike to 900.2, overshooting the 1.2 cell death threshold. This vector clears the tumor's apoptosis barrier by over 800 times. This level of precision is impossible when using standard array wrappers that average away structural outliers. It requires mapping exact microenvironmental forces at the nucleotide level. Explicit quantum electrostatics provides the mathematical framework required to engineer deterministic phase inversions.